I know what you're thinking. Finally, section 3.5, where we can analyze both tangential and radial accelerations. So here's the objectives. We want to understand the vector components that are associated with accelerated circular motion and use a little bit of trig to combine the radial and tangential components of this acceleration. So basically what we have going on here is we've got an object that is not only moving in a circle, but it's also going to be either speeding up or slowing down as it moves in that circular path. So let's consider the motion of a particle along a curved path where the velocity is changing both in direction and magnitude. What does that now mean about the direction of the acceleration? If you remember the last screencast, we looked at a diagram like this one here, where the object was simply moving in a circular path at a constant speed. So the velocity vector and the acceleration vector were perfectly perpendicular to each other. Acceleration was strictly towards the center of the circle, velocity was tangent to that. In this case, we're looking at a new diagram. Velocity is still going to be tangent to the circle. It always is. But in this case, your total acceleration is going to be at an angle that is something other than a 90 degree. In this case, we have an angle that's larger than 90 degrees. We could also look at a scenario where we have an angle less than 90 degrees. And what you'll notice is that if we were to put this problem on a coordinate system. Let's say that we actually draw an axis here. We want to draw an axis such that our velocity is along one axis, so there's tangent to the circle being one axis, and the other axis always has to be perpendicular to that. What you'll notice is that if we go back to our acceleration vector that's located here, you can clearly see that this acceleration vector has a component that is along this axis or towards the center of the circle, and it also has a component that is along this axis or that is along the velocity's direction. So part of the acceleration is causing it to move in a circle, that would be the centripetal part, and part of this acceleration is causing it to either speed up or slow down. In this case, because this piece is directly opposite the velocity, it's going to cause the object to slow down. These two components are called the centripetal acceleration, the piece causing it to move in a circle, and the tangential acceleration, or the piece causing it to slow down or speed up as it moves along the circular path. Now to actually find that acceleration, remember there's two pieces of it, so we need to find each piece. The tangential acceleration is simply looking at how it's changing the speed of the object. It's basically your dv dt. How is velocity or speed changing over time? For the centripetal piece, also called a sub r for a radial component of the acceleration, that's the centripetal acceleration of v squared over r. So the same thing that we did in the last section. So the radius here is going to be based on the curvature of that circular path. Again, you don't necessarily have to move in a perfect circle. You could instead move along a curved path, maybe something like this. In that case, we would focus on the piece of the circle that you're actually moving along. So in this case, we'd look at a radius of something like this. Along this part of the circular path, we'd sort of finish that circle and look at a radius of something like that. Now in this case, if we want to find our total acceleration, we have to understand that that acceleration has, again, two pieces, both the tangential and the radial. But each of those pieces, the tangential and the radial components to acceleration, are at right angles to each other. So your total resultant vector of these two would simply be using a Pythagorean theorem to find that. So that's where we get the equation of taking the square root of the radial component squared plus the tangential component squared. Let's look at an example of something like this. And part of this got cut off, so I will tell you what the problem is going to be. We're going to have a point on a turntable, and that point on the turntable is going to be located 20 centimeters from the center of the turntable. And it's going to accelerate from rest to reach a final speed of 0.7 meters per second over the course of 1.75 seconds. Now, at one particular point in time, we want to find the acceleration of that object. And again, the acceleration is going to include two pieces, both the radial, or a sub r, a sub c, and the tangential component. Let's start with the tangential component, because the tangential component, again, is just how velocity changes over time. We know that this object goes from 0 to 0.7 over the course of 1.75 seconds. So if we take final minus initial over the time frame, the tangential component of this acceleration comes out to be about 0.4 meters per second squared. For the radial piece, or the centripetal acceleration, we do need to know the v squared, which means that we're going to have to start by actually finding the velocity at this particular point in time. That can be easily done with your kinematic equations of Vf equals Vi plus At. Your final velocity is equal to the initial of 0 plus our acceleration, which we said was 0.4, multiplied by the time. We're looking at a point in time that was 1.25 seconds into the motion. So our final velocity of how fast the object is going when it reaches this point in time comes out to be about 0.5 meters per second. We can now use this in our centripetal acceleration equation to show that if we square that velocity and put it over the radius of 0.2 meters, remember we want to keep everything in SI units, so 20 centimeters will be converted to 0.2 meters, and we actually divide that out, we'd find that the centripetal acceleration is about 1.25 meters per second squared. And finally, if we want to find that total acceleration, we now recognize that acceleration has both the tangential component and the radial component, and we can combine those two in a Pythagorean theorem. So our total acceleration is going to be equal to the square root of our tangential piece, 0.4 squared, plus the radial piece, or the centripetal piece, of 1.25 squared. We're going to square those, add them, and square root them to get a total acceleration of 1.31 meters per second squared. So that's a quick example for you for what this looks like when you have both radial and tangential accelerations for an object moving in a circle.